Good afternoon. Today we're going to be proving the Pythagorean Theorem, which if you don't know, is that for any triangle of sides A, B, and C, right triangle, their sides can be related by the equation a squared plus b squared is equal to c squared. Now before we can prove the Pythagorean Theorem, we need to prove another algebraic equation, which is a plus b squared is equal to a squared plus 2ab plus b squared. Now to do this, we need to draw a square the side length is a plus b. Alright? And now we need to divvy up each side like this. So we're going to split it into a and b. We're going to put b and a here. Alright? And now we need to put b and a here. We're going to put a and b here. And what this is going to do is going to allow us to draw... Damn it, I did this wrong. Okay. Alright. Alright, so that should be B. That should be B, and that should be A. Okay. It doesn't really make much difference, it just looks nicer this way. So, what you can do with this is you can draw out these lines like this. It's more clear if I drew a better picture. And you'll notice we'll have two squares here. One is a squared, the area is a squared. One of the areas is b squared. And we're going to have two rectangles, both of area of AB. And so now we can say the area of the whole square is equal to the areas of each of the individual squares summed. So we can say that a plus b squared is equal to a squared plus b squared plus 2 of these, so 2ab. And now we get our first identity. And so to prove the Pythagorean theorem, it's quite similar. We have to make a square of also side lengths a plus b. I might make this that smaller. Side lengths a plus b, but how we're going to split each side is going to be slightly different. We're going to have a and b here, and we're going to have the sides sort of alternate between these a and b, like so. And what you'll notice that a and b corresponds with the right triangle, because of course the square, the angles of the corner of the square are right angles. And so we can make 4 right triangles out of this. The hypotenuse of C. Now for our original right triangle, it has 2 other angles, alpha and beta. Why not? Just call them that. And we know that for any triangle, all the angles added together is 180 degrees. But 90 of those degrees have already been taken up by the right angle. So we know that alpha plus beta is equal to 90 degrees. So we can use this in our square for a plus b squared. And we can note that alpha's here, beta's here, alpha's here, beta's here, alpha's here, beta's here, alpha's here, and beta's here. Now the angles of a line total up to 180 degrees. So for this line here, beta and alpha are already taking up 90 of those degrees. So we know that this angle here has to be a right angle, and it's the same argument for all of these. So we know that this C, this rectangle, whatever, of C is indeed a square, and we can say its area is C squared. Now we can say the area of each individual triangle is 1/2 times the base times the height, which is AB over 2. So each of these are AB over 2. So now we can say, just like we did before, that the area of the whole square is equal to the area of each individual square, or shape, inside it. So we can say that a plus b squared, which we know is a squared plus b squared plus 2ab. So let's write that down. Is equal to c squared plus 4 times ab over 2. Now you'll notice that the 2 and the 4 make a 2 out here, and that this 2ab and this 2ab can be minus from both sides and cancel out. And what you'll be left with is indeed the Pythagorean theorem, a squared plus b squared is equal to c squared. And that's all there is to it.